In this video, we're going to take a look at common types of chemical reactions found in biology. So next thing is the first law of thermodynamics. Now this states that the total amount of energy in the universe is constant, meaning that we can't create or destroy any energy. We can only convert it. So any energies that we're talking about, especially when we talk about endergonic or exergonic reactions, or the gaining or release of energy, that energy had to come from somewhere or is going somewhere. So oftentimes these types of reactions are paired together. So the endergonic reaction that needs energy will often happen simultaneously with an exergonic reaction. So the exergonic reaction releases the energy, the endergonic absorbs it, and the two reactions kind of feed off each other. So oftentimes as well we hear the term bond energies. This is a measure of covalent bond stability. So the more bond energy there is, it means the more stable that bond is, the more energy there's stored inside that bond. So when we're breaking and forming bonds, we have the release and the absorption of energy. So when we form a bond, we have a release of energy, because when we form that bond, it is more stable. So some of that energy is released that was kind of keeping those things stable. However, when we break a bond, there is a net absorption of energy, because there has to be energy put in to destabilize that bond to allow it to be broken. So we can see bond energies of different types of covalent bonds here between hydrogens and carbons and oxygens, noticing that the single bonds have less bond energy, meaning less stability, than the double bonds. So if we take a look at what that means, is if we have two reactants A and BC, and ultimately we would like to create products AB and C, what has to happen is this bond needs to be broken first. Well, there needs to be an input of energy to break that bond. So that is that activation energy. And as that activation energy is being achieved, we get into this transition state, meaning that the bond between BC hasn't quite broken yet, but the bond between AB has not formed yet. So what happens is the energy is going into breaking that bond BC. And then when we see this release down here, what's happening is as that bond AB is formed, there's more stability, therefore there is energy released for the products. So let's take a look at some specific examples of condensation or anabolic reactions. Now we've seen the creation of a peptide bond before between amino acids, so this should look familiar. So we know that it's a dehydration synthesis, so we need the hydroxyl from one amino acid and the hydrogen of another, breaking off, creating water, and the resulting elements bond together, creating a peptide bond. So in order to release that hydroxyl and hydrogen, we need to break that carbon-oxygen bond and that nitrogen-hydrogen bond. So we refer to the chart and see the amount of energy needed to break those bonds. So a total of 750 kilojoules per mole energy needs to be put in to break those two bonds. Now, what we are left with is a bond between the carbon and the nitrogen, or a peptide bond, and a carbon-nitrogen bond has 305 kilojoules per mole. So that amount of energy is released when that bond is formed. So overall, we have to put in more than is released. So anabolic reactions are endergonic because we had to put in 445 kilojoules per mole of energy. These are also called sometimes non-spontaneous reactions because there is a significant input of energy overall. So energy has to be found before it can happen. It's not just going to kind of happen on its own. So we should recognize those as familiar when we're going from those monomers to polymers. Now looking at hydrolysis or catabolic reactions, we know that when we have a bond and we have the addition of water to cleave that bond, and we end up with a hydroxyl group bound to one end and a hydrogen bound to the other, what has to happen is that initial bond needs to be broken. So in this case, it's a carbon and an oxygen that's being broken. So we refer back to the chart, and we see the amount of energy it takes. Now in terms of bonds being formed, that's a release of energy. So we have a carbon-oxygen bond being formed, and we have an oxygen-hydrogen being formed. So overall, a net of 818 kilojoules per mole being released. So we put in 359, we released 818, net output or release of 459 kilojoules per mole. So that's why catabolic reactions are said to be exergonic, because there is more energy being released from the bonds that have been formed. Sometimes catabolic reactions are known as spontaneous reactions because there's this net release of energy. It just takes a little nudge to kind of get going, and then the ball gets rolling with the net release of energy. The next type of reactions are oxidation, reduction, or sometimes called redox reactions. This is when there's a release or transfer of energy because electrons are moving from one substance to another. So when we have two substances here, we have what is called an oxidized compound and a reduced compound. So oxidation is the loss of electrons. So this green compound is oxidized because it is losing an electron. Then there is reduction. This orange compound is being reduced because it is gaining the electron. One way to remember oxidation, loss of electron, reduction, addition of electrons is through the saying, Leo the lion says grr. So loss of electrons is oxidation. Gaining electrons is reduction. So if you remember Leo the lion says grr, you should be able to remember what is happening when. Oftentimes redox reactions are coupled or paired together. So if we have substance A that is losing an electron, which is an oxidation of A, B is being reduced. It's gaining that electron. But then B loses its electron via oxidation to C. And then C, so here is reduced, and then it is oxidized. So substances aren't only ever reduced or oxidized. Both can happen. So what happens here is B pulled the electron from A, C pulled it from B, and D pulled it from C. So D is known as what is the strongest oxidizing agent, meaning that it can pull that electron or force the oxidation of C. It's the strongest pull on that electron. So sometimes you will also see those electrons don't just move as electrons, they move attached to a hydrogen. So you might see a H with that hydrogen, and it's actually the hydrogen that is transferred along with its electrons. So in this case, that hydrogen is moving along, causing the redox reactions. Most common example of redox reactions in humans is the electron transport chain. This is why we breathe. The oxygen that we breathe in is the final electron acceptor. It is pulling the electrons from this molecule, which pulls them from here, which pulls them from here. Without the oxygen, there is no pull of electrons, no transfer of energy, no ATP formed. Neutralization or acid-base reactions are one that you should have seen before in classes, and recognize it as an acid and base yields salt and water. Well, we don't always want the complete neutralization. As we've seen earlier, enzymes have specific pHs that they need. So if we neutralize everything, a lot of reactions would stop occurring. So this is where substances called buffers come into play. Now, a buffer minimizes the changes in concentration of hydrogen ions or concentration of hydroxide ions in a solution. So that means it minimizes the change of becoming acidic or basic. And what happens is you have these molecules known as buffers that can donate or accept hydrogen ions. So by donating hydrogen ions, they make an area more acidic. By accepting or absorbing them, they are making an area less acidic or more basic. So we can see this with our blood and our body tissues, is when we absorb carbon dioxide, it reacts with the water to create carbonic acid. Well, carbonic acid can then donate those hydrogen ions if it needs, becoming a bicarbonate ion, which could then reabsorb those hydrogen ions. So what that looks like is carbonic acid and bicarbonate ion. This is our buffer system here. Is if we look at this and we say we have carbonic acid, if there's a rise in pH, meaning the numbers get bigger, meaning it's becoming more basic, what will happen is the carbonic acid will donate its hydrogen ions, making it come back down a little bit. Whereas if there's a drop in pH, meaning it's becoming more acidic, there are more hydrogens in the environment, the bicarbonate ion will absorb or attract those hydrogen ions and become carbonic acid. They will bind them in a compound. So the reason this is so important is if we look at our blood pH levels, tiny little shift can actually cause death. So buffers are very important to maintain our biological systems.